Hi, my name is Alder Whiteford, and today we're going to be working with inductive proofs. In this video, we're going to be looking to prove that 9 to the n minus 1 is divisible by 8 for all n is greater than 0. Before we get started, though, I would like to also argue that n exists in integers. The reason why I say this is because if we were to plug in a non-integer for n, let's say 1.2 for example, the output in most instances will also not be an integer. In the case of our example, the number will be roughly 12.96. As 8 is an integer, though, we know that 9 to the n minus 1 must be an integer for it to be divisible by 8. Let's move on to the belief phase. It is important that before we work through our inductive proof, we convince ourselves that what we are trying to prove is true. If we are assuming that 9 to the n minus 1 is divisible by 8 for all n is greater than 0 and n exists in integers, we know that for every subsequent n, this claim should hold true. Therefore, when n is equal to 1, and n is equal to 2, and n is equal to 3, and so on, the 9 to the nth power minus 1 should be divisible by 8. Let's start with n equals 1. If we replace 1 for n, we end up getting 9 to the 1 minus 1 is equal to 8, which, as we know, is divisible by 8. Let's do the same thing for the numbers 2 and 3, so we can really cement this idea in our minds. As you can see, both of these values also produce an output that is divisible by 8. In doing so, we have somewhat convinced ourselves that this statement is true given the restrictions n is greater than 0 and n exists in integers. The last thing we need to consider before we move on to our inductive proof is deciding what type of induction is appropriate for this problem. I'm going to argue that in the case of our problem statement, we will need to use weak induction. This is because, given the mathematical statement, we are simply trying to prove that 9 to the n minus 1 holds true for an arbitrary nth step. Therefore, the inductive proof only needs to consider the value that comes before it to prove that the statement holds true for all n is greater than 0 and n exists in integers. By this logic, we'll be using weak induction for this problem. To begin our proof, we will first write out our claim. For this part of the inductive process, we can simply pass in the thing we want to solve, which is 9 to the n minus 1 is divisible by 8 for all values if n is greater than 0 and n exists in integers. We will set this equal to p of n for the purpose of our proof. Now that we have our claim, we want to consider the base case. In specifically weak induction, the base case is always the first valid value of n. As n is greater than 0 and n exists in integers, we know what the base case will consider when n is equal to 1. To solve the base case, we can simply plug in 1 for n. Here we'll get p of 1 is equal to 9 to the 1 minus 1, which is equivalent to 8. As 8 is divisible by 8, we have proven that our base case holds true. With the base case out of the way, we will now formulate an inductive hypothesis that will help us prove that p of k implies p of k plus 1. As we're working in weak induction, we are going to assume the following. N is equal to k, in which the same restrictions apply. K is greater than 0, and k exists in integers, and also p of k is equal to 9 to the k minus 1, which is divisible by 8. Based on our assumption that 9 to the k minus 1 is divisible by 8, we can set p of k is equal to 9 to the k minus 1 equal to some arbitrary integer x multiplied by 8. This is because if 9 to the k minus 1 is divisible by 8, it must be equal to some integer multiplied by 8. Using our inductive hypothesis, we will now prove that p of k implies p of k plus 1. We are going to begin by writing out what p of k plus 1 is equivalent to based on our hypothesis. Assuming that p of k is equal to 9 to the k minus 1 is divisible by 8, we can plug in k plus 1 for k, which gets us p of k plus 1 is equal to 9 to the k plus 1 minus 1 is divisible by 8. Because we are trying to prove that p of k implies p of k plus 1, it is going to be beneficial to manipulate this equation so that we are only dealing with 9 to the k and not 9 to the k plus 1. Luckily for us, exponential rules allows us to remove the plus 1 from the exponent and convert the equation to be p of k plus 1 is equal to 9 times 9 to the k minus 1 is divisible by 8. This is where our work in the inductive hypothesis comes in. If we were to take 9 to the k minus 1 equals 8x and simply move over the negative 1, we end up with 9 to the k is equal to 8x plus 1. With 8x plus 1 being equivalent to 9 to the k, we can plug in 8x plus 1 for the 9 to the k over here. By simple distribution, this becomes 72x plus 9 minus 1 is divisible by 8, which becomes 72x plus 8 is divisible by 8, which can finally be rewritten as p of k plus 1 is equal to 8 times 9x plus 1 is divisible by 8. At this point, we know that the statement is true as 8 times 9x plus 1 includes 8 as a multiplying factor, and therefore is cleanly divisible by 8. We have now proven that p of k implies p of k plus 1. Now that we have proven that p of k is equal to 9 to the k minus 1 is divisible by 8 for all k is greater than 0 and k exists in integers by our base case, and that p of k implies p of k plus 1, we can confidently state that 9 to the n minus 1 is divisible by 8 for all n is greater than 0 and n exists in integers.